Hello people, this is part 2 of the Minesweeper mini-series on this channel. In this video I'm going to cover a trick which I call reduction. Before, you always looked at numbers which have the same amount of cells next to them. For example, this one only has one unrevealed cell next to it, while this 5 has 5 unrevealed cells next to it. This basically then says that these cells need to have a mine because the mine can't be anywhere else. These cells are all revealed already. Well, this method works and is enough for some simple games. For some more advanced games, this method isn't enough. Some games just can't be solved with only this method. This is why I'm going to look at another method, which I'll call reduction. How do reductions work? Basically, let's use this example here. We set up so-called fields. For example, this one here has 2 adjacent cells, so we create a field which is 2 cells wide, or 2 cells big. And this one here has a field with 3 cells. Now, this field basically says to us that the mine, which this one points to, is somewhere within the red field, while for the green one, in the green field, basically the one here points to a mine in the green field, somewhere here. Now notice the red field is within the green field. This is very helpful because we know that somewhere in the red field there is a mine. So basically, these 2 cells have the mine, right? But this cell is ignored. This helps us because then we can cross out these cells as having a potential mine, and then for the larger number, which is the one here, we can subtract it from the number of mines that we think are in these 2 cells, which is 1. So we do 1 minus 1, which is 0. Now we kick out these cells from the field, from this cell, and this leaves us with only this cell here. And since 0 is, well, basically nothing, 0 mines, this cell doesn't have a mine. And so we can reveal it as so. And this will never have a mine. Here is a short overview of what we did. Continuing on, we can still apply this method here. As we can see, this one here creates a field that looks like so. So basically all the adjacent cells. The one here creates a field as so. Here. You can see that the red is contained within the green. So we can apply the reduction again. We can basically kick out the green from the red and reduce the number by 1. Thus, this green cell here must not have a mine because it's 0 here. So we can reveal this area here. This method doesn't only show us if a cell doesn't have a mine, it can also show us if a cell does have a mine. For example, this. We see that 1 produces a field like this, and the 2 produces a field like this. Right? So we apply the reduction again. We kick out the green from the red. This leaves us with a red that looks like so, and the green cell is here. And the 2 is then reduced to 1. And since we have only 1 cell in the field and 1, if we look back to our previous video, this means that this has to be a mine, right? Because we only have one cell, right? These cells have been kicked out from the field. And thus we can place a flag here. Well, here are some more advanced examples. For example, this 2 here as a field which encompasses this, this, and this cell. Now this cell, we're very certain, already has a mine, which means we can then subtract this 2 by 1. We've already found a mine here. So now the field is only here and here, right? And this field has a value of 1, right? There's only one mine in these two cells. Now this 1 here encompasses all of these 5 cells, right? And we can see the field from 2, which is only here now and here because we basically took this one out, is encompassed by the field of 1, right? Encapsulated. So we can take these 2 cells from the field of 1, right? So now here is 0 with this as its field. And that means that these 3 cells are free. So you can reveal them, right? Now in this example, now the 2 here, of course this could be a mine, right, because it's 2, but let's just imagine that there are more cells in this direction. Here we can do another thing. We can use reduction again. If you see 2 here, we can subtract it by 1 because, well, there's a cell here. So basically the field which was here now becomes a field that's like this with a value of 1, right? This cell, well, this number, has a field with these 3 cells. And we can see that the field, which is produced by this 1 here, well, it's 2, but we subtracted it to 1, is encapsulated by the field that this 1 produces. So we can kick out these 2 cells, and this cell basically becomes free because this becomes 0, right? It's basically just like our previous example. I'm now going to play an example game, which is harder than last time, and using this method. So we start the game by clicking X. Here we go. I already have to use the method. We have 2 1s here, and using reduction, we can see that these 2 cells have 1, right? They have like a field of 1, and these 3 cells have 1 mine, right? This means, because these 2 cells have a mine, that this cell doesn't have a mine, right? Because this 1 here already says these 2 must have a mine. Now, here you can use reduction again. It was like an example from before. This is free, and this is free, right? Here you can place some mines. Continue on a bit. Basically using the methods that we had from before, right? I'm only now just using the method from the first video where we have the same amount of cells, or unrevealed cells, as the number. Here we can use reduction again. We have a 1, which means there's a mine here, and we have a 2 here, which means there are 2 mines in here. Since you already know these 2 have 1 mine only, this leaves out 1 mine for this 2, which means this has to be a mine. And then click the 2 here, and we continue. You can apply reduction again. We have 2, and we have these 2 2s. This 2 has a mine here, and this 2 already has a mine here, which means both of them are basically 1s. So we have 1 mine here and 1 mine here. This means this is a free cell. Again, we can use reduction here. This makes this a free cell. And we can use reduction here, right? We have a 2 here, which means this becomes a 1 because of this mine, which means there is only 1 mine in these 2 cells. No, wait, no, I can't. Oh, no, wait, we can, because there's a 2. Okay. Which means these cells need to be freed because, right, because these 2 cells, they have 1 mine, right? And this 2 becomes 1 because of the already found mine here. And this 2 already also becomes 1, right? And I already know that these 2 cells must have a 1, right? So this 2 here, or well, this 1, which we calculated, also points to the mine, which is here. So these cells have to be free then, right? Okay. Can continue on. We can use reduction again. This makes this a mine. We have another example of reduction, but with subtraction. So this is basically 1, and this is 2. Here we have a little curveball, but this is basically reduction again. We have a 5 here, which has 1 mine here, right? Because we have now 4 mines which are found here. And then 5 minus 4 is 1, so this is 1. And here we have 3, and 2 minus, 3 minus 2 is 1. Right? So we have 1 mine here and 1 mine in these 4 cells, which means that these 2 cells must be free. Right? This is this. Using reduction again, we find that this cell has a mine. Reduction. And we're done. Oh, for fuck's sake. Okay. As we see, the method is very helpful. And if we didn't have the method here, then we couldn't have already, or we probably would have already exploded here, because we didn't know what cells to open.